Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss steam generation in plants. Before starting this, let us have a look on boiler nomenclature. A mud drum is the bottom part of boiler using thermosiphon water circulation. Steam drum is where water and steam are separated. FD fan, also called FD blower, supplies combustion air into a forced draft reboiler. Waste heat boiler derives heat from convective section or process pump around or product streams. Demineralization plant is where boiler feedwater is treated using ion exchange resin. Hot lime softening is an older method to reduce the mineral content of boiler feedwater. Coordinated phosphate pH control is an old method of treating water to reduce mineral content in BFW, causing precipitation of hardness salts as free-flowing sludge, used for power plant boilers. Deaerator is used to minimize oxygen content of BFW by steam stripping. Oxygen scavenger is a chemical used to remove residual O2 after BFW has been through Deaerator. Condensate is the water recovered for reuse after steam has been condensed. Condensate polisher is the clay diatomaceous earthbed or filter used to remove oil from steam condensate. Silicates are minerals in steam that plate out on steam turbine blades. Steam quality is a measure of the moisture content of steam. Saturated steam is cooling steam from its saturation temperature, at constant pressure, causes 100% condensation of saturated steam. TDS are total dissolved solids. Blowdown is draining several percent water from boiler to control TDS content of steam. Intermittent blowdown is used to control suspended solids from mud drum of power plant boiler. Superheat is heat added to saturated steam. Economizer is used to preheat cold BFW. An important feature of steam generation in a process plant is steam condensate recovery. This is usually a function of proper design of the steam condensate controls on individual steam heaters and reboilers, as well as proper design on the condensate recovery system. Experience shows a reasonably good condensate recovery rate in a large, complex refinery is 70%. A substantial portion of the steam is used for process steam stripping, purging vessels, instrument connections, flare dispersal, and other non-recoverable uses. Thus, the 70% rate is really rather good. On the other hand, 30% condensate recovery as a percentage of the steam generation rate is rather bad and represents sloppy operations and bad condensate recovery design practices. Very approximately, 10% of the cost of steam generation could be saved by recovering the condensate. The condensate contains few silicates, thus no blowdown is needed, no chemical treatment or deaeration is required, and no energy that would otherwise be used to preheat the boiler feedwater will be wasted. Boiler blowdown rate. Although boiler feedwater, BFW, has been treated to remove minerals, residual contaminants, carbonates, silicates, are still present. These minerals, especially the silicates, are bad, as to some extent they are going to be entrained into the generated steam. The biggest problems with entrained silicates TDS or total dissolved solids are drying out on the steam superheat coils, which then fail due to localized overheating, which results in superheat tube failure. Depositing on turbine blades. The deposits eventually get so thick that they break off and unbalance the rotor. Resulting vibrations then cause the turbine to trip off, and stress corrosion of the blades causing sudden failure. Fouling of vacuum system ejector steam nozzles. The TDS content of BFW should be minimized by upstream treating. In former days, hot lime water softening was employed. In most modern process units, ion exchange resin is used to demineralize BFW. Blowdown is the water that is drained out of the boiler to control the accumulations of TDS or silicates in the boiler. Some people drain 10% of the makeup BFW flow. Two types of blowdown from a boiler are used, continuous blowdown from the steam drum and intermittent blowdown from the mud drum, both will reduce silica. Note that with the continuous blowdown, heat recovery equipment may be economically justified. Continuous blowdown. This blowdown water is best not drained from the very bottom of the steam drum. The concentration of silicates is 10 times higher at the steam-water interface than it is at the bottom of the steam drum. I've made the mistake in designing waste heat kettle-type boilers of locating the drain on the bottom of the kettle, which is wrong for the same reason. The correct drain location is somewhat below the minimum water level in the boiler steam drum or in the kettle-type boiler. TDS in the blowdown is based on what the steam will be used for. A typical value is 1,500 ppm. If steam from a kettle waste heat boiler will be used saturated, for heating, reboiling, or stripping, then the TDS content of the steam is not particularly critical. If steam is used to drive turbines or will be superheated, then the TDS content of the steam is quite important. A good target for silica is 0.02 mg per liter silica in steam used for turbines or for a boiler operating from 300 psig to 600 psig. 0.4 total caustic alkalinity as milligram per liter of silicon dioxide in BFW. Intermittent blowdown. This blowdown from the mud drum of a boiler is usually once a shift via manually operated valve. If this is automated, it is important to have the valve full open for short periods to keep the valve clear and unblocked. Types of steam generating equipment. These pictures illustrate the three types of steam generating equipment that are used in process plants. Most process units do not have the boiler shown in picture. Water flows via thermosiphon circulation, that is, the density difference between the steam drum and the mud drum. This is the kind of design used for a large boiler of the type found in the utilities department of a refinery or power plant. This picture is a convective section heat recovery forced circulation boiler. Many process-fired heaters have this feature. Hot flue gas from the radiant section is exchanged against BFW to make steam. A good water circulation rate is 10 times higher than the steam generation rate. Vaporizing 20% of the circulating water is still okay. Vaporization rates above this level will eventually cause convective section tube failures, as will even very short pump outages. This picture is the very common kettle-type waste heat recovery boiler. There is no water circulation. The tubes must be always covered by water. Allowing the upper rows of tubes to be uncovered will lead to uneven thermal expansion of the tube bundle and damage due to distortion of the uncovered tubes. If the BFW level is too high, this will cause water and silicate carryover into the evolved steam. This sort of carryover leads to more steam turbine vibration failures than any other cause. It's one of the major problems in the process industry. Controlling steam drum levels. Ordinary level control does not work in steam drums or kettle boilers. The problem is the lower density of the boiling water as compared to the greater density of the non-boiling hot water in the external level. Sensing chamber. The boiling water will be at a 10 to 50% higher level inside the steam drum than the water in the level sensing chamber or gauge glass. There are two ways of dealing with this problem. 1. The conventional method is to get a sample of steam condensate and measure it for TDS. If the blowdown water has a TDS of 1000 ppm and the sample has a TDS of 30 ppm, then the moisture content of the steam is 3 weight%. The assumption is that the TDS is totally due to entrainment. 2. Other method, which hopefully you will agree is better, is explained in picture. Assume initially the 400 psig steam is dry but saturated at 450 degrees Fahrenheit. Depressuring this steam through valve A will reduce the steam temperature to approximately 360 degrees Fahrenheit. As the boiling water level rises and entrains into the 10-inch steam line, the temperature of the vented steam at T1 drops to 300 degrees Fahrenheit. Latent heat of water equals 1000 BTU per pound. Specific heat of steam equals 0.5 BTU per pound per degree F. Therefore, The water content of the 400 psi steamed sat phase 360 degrees Fahrenheit minus 300 degrees Fahrenheit times 0.5 divided by 1000 is equal to 3 weight%. 3 weight% water in steam is a lot and would be considered poor quality steam. Superheating steam. One supplier had some very bad experiences with superheating steam furnace convective tube failures. The cause of tube failure was overheating of the tubes due to hardness deposits precipitated from poor quality steam. The convective section tubes will typically be carbon steel, which fails at about 1000 degrees Fahrenheit. The one case I have in mind occurred at a large refinery in northern Spain. The supplier had supplied the retrofit design for their crude unit distillation tower fractionation trays. The startup went well, and his new tray design worked fine for 2 days. Then the furnace steam superheat coil failed, and the unit was shut down. During the second startup, the operators inadvertently filled the tower to the top with crude oil and damaged all the trays. The tower would no longer fractionate. The worst part about the whole incident is not that supplier was blamed for client's operating errors. It was that the steam was being superheated for no purpose. All of the steam was being used for hydrocarbon product stripping, where steam superheat is not important. For example, product stripped is 450 degrees Fahrenheit gas oil. Steam rate equals 2 weight% on feed. Superheated steam equals 650 degrees Fahrenheit. Specific heat of steam equals 0.5 BTU per pound per degree F. Specific heat of gas oil equals 0.65 BTU per pound per degree F. Therefore, the temperature increase of the gas oil due to the superheated steam is 650 degrees Fahrenheit minus 450 degrees Fahrenheit times 2% times 0.5 divided by 0.65 equals 3 degrees Fahrenheit. The 3 degrees Fahrenheit is hardly worth the investment in the superheat coil. Superheating steam for rev boilers and steam heaters is mostly a waste, as it's a standard industry practice to inject condensate into the steam to bring the steam back to its saturation temperature. Superheated steam does not transfer heat as well as saturated steam. Hence, the de-superheating stations. As there is typically another convective section, usually BFW preheat, above the steam superheat tubes, no net energy savings result from steam superheat. The maximum allowable superheat coil outlet temperature is 700 degrees Fahrenheit to protect the carbon steel tubes from failure. At low steam generation rates, I have seen furnace firing rates and thus heater charge rates reduced to keep from overheating the steam above 700 degrees Fahrenheit. If the steam is not used eventually to drive turbines, or as a reactant in a catalytic process, steam methane reformer for hydrogen or ammonia production, then the heater capacity is being limited for no logical reason. Condensate polishing. The recovered steam condensate may often be contaminated with oil. As the condensate will flow into the lower portion of the deaerator, this possible oil contamination must be removed to protect the boiler tubes from the formation of non-wettable films on the heat transfer surfaces which interfere with the detachment of bubbles so that the boiler tube surface is then not sufficiently cooled by boiler water, thus causing severe corrosion and tube failure. Low-level oil contamination, 5 mg per liter, can be removed by passing the condensate through clay or diatomaceous earth, either as a bed supported by anthracite or diatomaceous earth precoat filters supported by filter paper, porous stone, or wire cloth, etc. In addition, a small amount of earth is fed continuously with incoming condensate at the filter inlet. The filter cake is later removed by backwashing and rinsing. Condensate with heavy oil contamination can first be treated by oil skimming or settling, or otherwise must be simply sent to the effluent treating facility. Note that although it is beneficial to keep condensate hot in the condensate recovery system so as to reduce the solubility of air and oxygen, as dissolved oxygen being a major cause of corrosion in condensate piping systems, oil is easier to remove from condensate when it is cool. Thus, cold boiler feedwater is often used to cool the condensate stream, or air cooling is also sometimes used. Oil settling operations are best carried out below 100 degrees Fahrenheit. Although skimmers and diatomaceous earth precoat filters can operate at higher temperatures, that is 175 degree F, the temperature limit is usually based on the temperature at which silica dissolves. Incidentally, the typical optimum pH of water in a boiler is close to 9 to retard boiler tube corrosion, shown in picture. Coordinated phosphate pH boiler water treatment. An engineer described an archaic form of boiler feedwater treatment that had saved the day for the utility plant in the refinery where he had been working when the refinery demineralization plant froze one winter, resulting in seriously restricted flow and a great shortage of boiler feedwater. The technique and chemistry are described by a paper written by George Gibson Betts, although according to Mr. Gibson, it was apparently first introduced in 1942 by S.F. Whirl and T.E. Purcell of the Duquesne Light Company. Engineers said that they were able to treat raw city water and add it to the treated water for boiler feedwater simply by following the operating guidelines set by the Coordinated Phosphate pH Control Chart. It works by causing hardness salts to be precipitated out as free-flowing sludge, calcium as phosphate, magnesium as hydroxide or silicate. This is achieved by continual additions of sodium phosphate and maintenance of pH within guidelines as set by the Coordinated Phosphate pH Control operating envelope, which depends on the operating pressure of the boiler for which the feedwater is required. The alkalinity pH is adjusted by additions of sodium carbonate or sodium hydroxide. Demineralization of BFW. The main advantages of cation-anion ion exchanger resin demineralization over phosphate treating or hot lime softening of boiler feedwater is the superior reduction of silicates and steam. Silicates deposited on steam turbine blades may lead to a loss of turbine efficiency and vibration, and also stress corrosion and sudden failure of the blades. Such a demon plant consists of a cation exchanger resin bed followed by an anion exchanger resin bed. These resins look like small yellowish plastic beads and remind me of fish eggs shown in picture. The raw water flows downward through the cation exchange resin bed, where the metallic ions are removed. Then, in a typical installation, the partly treated water flows into a large degassing vessel. Next, the water flows downward through the anion exchanger resin bed, where the silicates and carbonates and other such anions are removed. Periodically, the resins have to be regenerated to strip out the absorbed ions. The regeneration solution, dilute acid for a cation bed, dilute alkali for an anion bed, flows in an upward direction. This is followed by a rinse step using treated water. Completion of the rinse is typically monitored by conductivity probes. The arrangement in picture shows the operation of these resin beds in pairs. Basically, this means that 6 vessels are in service at a given time, but each pair is at a different stage in the cycle. 2 absorbing ions, anions and cations. 2 in regeneration mode. 2 in rinsing mode. It is important to avoid stirring up the resin during the regeneration step. The main objective of the regeneration step is to leave the purest resin at the bottom of the vessel. This will then polish the downflowing water when the bed is returned to its ion exchange service. A slight back pressure, using air, is typically employed at the top of the beds to hold the little beads in place during regeneration, and works best after first draining the bed down by about 1 foot below the top of the resin bed. It is also possible to lose the beads from the ion exchange vessels during the regeneration and washing steps if the resin beds are not held down properly during this step. Improper demineralization will also leave carbonates in the BFW. These carbonates will break down in the boiler to produce CO2. CO2 contaminates the steam supply to reboilers, where it is trapped. The CO2 accumulates and dissolves in the steam condensate to produce corrosive carbonic acid, resulting in tube failure in the reboiler tube bundle. Effective air preheat on boiler capacity. One of the first questions that many people ask is, Our utility plant operators have observed that when they preheat their boiler combustion air from 20 degrees Celsius to 220 degrees Celsius, steam production drops by around 3 or 4%. They are forced to reduce the firing rate because the radiant section of the boiler starts to overheat. With the radiant section just as hot with or without the air preheat, I would think that steam production would remain constant, so why would it drop off? The answer is that air preheat requires less fuel gas firing, and thus, less flue gas and hence less heat pickup in the convective section. While the radiant section heat transfer rate will remain constant, the heat transfer rate in the convective section will drop in proportion to the reduced fuel gas fired. A 200 degrees Celsius, 220 to 20 degrees Celsius of air preheat will save 10% of the fuel and thus reduce the flue gas flow by the same 10%. As the convective section duty is typically 30% of the total boiler duty, a 10% reduction in the flue gas rate will reduce total boiler steam production by 30% times 10% equals 3%. Of course, you are also saving 10% of the fuel gas consumed for each pound of steam production, so perhaps the 3% boiler capacity reduction was acceptable. That 3% is the price we have to pay for energy savings. Combustion air preheat in boilers, which are limited by excessive radiant section temperature or hot tubes, will always lose steam production capacity due to the air preheater. Adjusting excess O2. At an oil refinery, I first learned how to optimize the excess oxygen content of the flue gas from a boiler. The fired boiler was equipped with a forced draft FD fan. Due to mechanical deficiencies of the FD blower, the combustion air supply was limited but constant. The boiler produced 650 psig steam, which was in short supply in the refinery. Hence, the boiler was operated to maximize steam production. The utility plant operators would routinely adjust the fuel gas supply to maximize steam production. There was an accurate oxygen analyzer on the flue gas stack. It typically recorded several % oxygen in the boiler stack. However, this O2 value was ignored, and correctly so, by the operators. They simply adjusted the fuel gas rate, which had a variable heating value, to maximize steam production with a fixed amount of combustion air. If, on the other hand, they had been trying to produce a fixed amount of steam, then they would have adjusted the airflow to minimize fuel gas consumption in the boiler. The listeners will note that I emphasized the word several, rather than stating a target O2 range in this example. There is no such range. The optimum O2 in the stack is whatever it is to maximize steam production. Which means, the O2 analyzer served no function in the control of this boiler. And that statement is, in general, true. Deaerator operation. Being born on Earth, I grew up unaware of the true nature of oxygen. Submerged in a sea of N2 and O2, I was ignorant of how unique oxygen is in the universe as a whole. Except on our home planet, oxygen does not exist in its free state. It's combined with H2, carbon, or sulfur. As a young process engineer, I was surprised to learn that oxygen is a terribly corrosive element. It must be precluded from most process environments, otherwise product degradation and corrosion will result. In particular, all O2 must be removed from BFW. This is done either with a chemical O2 scavenger or with steam stripping. Stripping air out of BFW is relatively inexpensive compared to the use of chemicals. A deaerator shown in picture is used to remove oxygen. The more efficient the deaerator, the less scavenger chemical treatment is required. Residual O2 in the deaerator effluent BFW is determined by a field titration kit, and the oxygen scavenger chemical addition rate is adjusted accordingly. The steam and cold deaerator make up water mix in the small stripping section shown in picture. Most of the steam condenses typically 90% to heat the cold water, 120 degrees Fahrenheit, to its boiling point temperature, 250 degrees Fahrenheit, at the deaerator operating pressure of 15 psig. The rest is vented to the atmosphere. This vented steam is being used to strip out the residual O2 in the cold water feed. Note that there is sometimes a second, hotter feed to the deaerator, in addition to the cold water feed to the stripping section. This secondary feed is steam condensate, which having already been steamed, bypasses the stripping section. The exception to this generalization is steam condensate recovered from turbine exhaust vacuum surface condensers. Such condensate may have been in contact with air that has been drawn into the surface condenser shell and thus may have to be deaerated again. As noted above, liquid hydrocarbons must be removed by a clay polishing step to prevent oil accumulation in the deaerator, or laydown of a non-wettable film on boiler tubes. In the event that there is too much residual oxygen in the deaerator. Effluent, the flow of vented steam from the top of the deaerator should be opened. However, often there is no vent valve, but just a fixed orifice vent. Or perhaps the supply steam control valve is 100% open. Someone had the latter problem at the refinery. The refinery was spending a small fortune on the oxygen scavenger chemical, pyridine. All engineer did was to lower the deaerator set point pressure from 18 to 13 psig, and the residual oxygen in the effluent VFW dropped by an order of magnitude. Anytime the steam inlet control valve becomes fully open, the deaerator temperature, pressure, and water level will become unstable, and the deaerator stripping section will flood. Flood in the sense that boiling water may erupt from the atmospheric vent. Boiler feedwater preheat. The optimum feed temperature to a deaerator is the boiling point of water at the deaerator pressure. Typically, 230 degrees Fahrenheit to 240 degrees Fahrenheit. However, in many of the plants, VFW to the deaerator is heated to 160 degrees Fahrenheit to 180 degrees Fahrenheit by heat exchange with process pump-around or product streams. As a young engineer, I had learned that cooling water should not be heated above 125 degrees Fahrenheit to 135 degrees Fahrenheit to avoid laydown of hardness deposits inside the tubes of water-cooled exchangers. What I had failed to grasp was that once water has been through a demon plant, there is no restriction on how high a temperature that water can be heated. The effluent from the deaerator, 230 degrees Fahrenheit, will then typically flow to the boiler's convective section, Economizer, zone. This usually consists of 4 to 6 rows of tubes at the top of the convective section, where the BFW is heated to 350 degrees Fahrenheit to 450 degrees Fahrenheit. If the boiler is firing high sulfur fuel oil, 2 to 4% sulfur, this may be a problem. The dew point of H2SO4 in the flue gas may easily be as high as 450 degrees Fahrenheit. The 230 degrees Fahrenheit water inlet may cause the flue gas temperature to drop below 450 degrees Fahrenheit. This will precipitate a weak H2SO4 mist, which will aggressively corrode the fins or studs of the economizer tube bank. If low sulfur, less than 100 ppm H2S is being fired, H2SO4 corrosion should not be a problem. For boilers firing fuel oil, bunker, it's best to preheat the BFW externally to perhaps 350 degrees Fahrenheit to protect the boiler's economizer convective tubes from corrosion. If a small amount of vaporization occurs in the preheat exchanger, this should not compromise the operation of the economizer, provided that there is only a single inlet to the economizer section. Boiler thermal efficiency. To estimate the efficiency of fuel to steam, 3 factors are involved. 1. Approximately, for each extra 360 degrees Fahrenheit or 200 degrees Celsius in stack temperature, boiler efficiency drops by 10%. 2. Approximately, for each extra percent of stack O2, boiler efficiency drops by 1%. 3. For small package boilers, 50,000 pounds per hour, boiler external ambient heat loss is approximately 2%. Thus, for a small boiler with a 600 degrees Fahrenheit stack, 5% O2 in the flue gas, boiler efficiency is 100% minus 15% minus 5% minus 2% equals 78%. Of course, the overall boiler plant efficiency will be lower due to steam leaks, Power to drive FD and ID fans. Power to drive BFW pumps. Steam tracing for freeze protection. Energy consumed in Demon and Deaerator. Power to drive raw water and condensate recovery pumps. Plant lighting and instrumentation. Finally, did you know that for each BTU worth of electricity, 3 BTU worth of steam are required? Sloped demister. On many boiler steam drums, there is a sloped demister to suppress entrainment and hence improve steam quality. However, if this demister becomes partly fouled with hardness deposits, it probably does more harm than good. In such cases, I would probably discard the demister rather than replace it. If you feel you have been doing a good job on level control in the boiler, but steam quality is still poor, you should consider this possibility. Entrainment of high TDS boiler feedwater into steam from a boiler is promoted by excessive pH. Caustic is often added to the feedwater to reduce corrosion. However, if the pH increases much above 10.5, then the boiler tends to foam, and hardness deposits are carried over into the steam. Hardness deposits degrade the performance of steam ejectors, steam superheating coils, and steam turbines. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.